Bismillahirrahmanirrahim. Assalamu alaikum. We were talking about Perceptron classifier. In the previous video, we concluded with this summary of Perceptron classifier. This is a model of a Perceptron classifier which we can use to carry out binary classification. We have d number of input features x1, x2, xd, and we multiply each input with different real valued weight w1, w2, and wd. And we also introduce this constant input to absorb this bias term at the input instead of considering it as a threshold at the output. So this block is simply aggregating the weighted sum of the inputs, and if this weighted sum is greater than or equal to 0, output is 1 and 0 otherwise. So W transpose X is simply inner product between the weights and the input, and the inputs including this constant input. And we also summarized that if we use -1 to denote the second output instead of 0, this all can be compactly written by as simply sign of Y transpose X. So if Y transpose X is greater than or equal to 0, Y is 1 and -1 otherwise, right? Okay, in this video we will talk about perceptron learning algorithm, that given the data, how can we learn these weights, or how can we have a hyperplane that separates linearly separable classes of our data, or how can we find a hyperplane that separates the classes in the feature space, right? We will start with the perceptron algorithm, and then we will talk about the geometric intuition and interpretation of the algorithm. We assume that we have n number of inputs and the classes are linearly separable. Usually we use 0, 1 to denote these two binary classes, but without loss of generality, we can also use -1 and 1. Here we will stick to this -1 and 1 to denote the label of two classes. We have this perceptron classifier, and we're assuming that we have a data which is linearly separable. So if W transpose X is greater than 0, we choose 1 as a label. W transpose X is equal to, if W transpose X is less than 0, we assign -1 to the label. And we assume that we have this linearly separable data. We want to find this hyperplane W transpose X is equal to 0. Given classifier, given the linearly separable data, we want to find this hyperplane. The key idea in finding this hyperplane is that yi W transpose xi is greater than 0 for every xi yi in the data. How do you interpret this? See, for all these red points, so that W transpose X is greater than 0 and Y is 1. When I multiply Y with W transpose X, I will get something greater than 0. Okay? So for all these blue points, W transpose X is less than 0 and Y is equal to -1. When I multiply Y with W transpose X, this is going to reverse the inequality, and I will get Y, which is -1 W transpose X greater than 0. So for every data point in my data set, I will have yi into W transpose Xi greater than 0. It simply means that Xi is on the correct side of the hyperplane. If all the red points are in the region where W transpose X is greater than 0 and all the blue points are in the region where W transpose X is less than 0, we have a separating hyperplane W transpose X is equal to 0, right? So building on this key idea, we will develop a perceptron learning algorithm. So algorithm looks like this. Let me explain. So we initialize weight vector, which is w is equal to 0. We can also use some random value of w. And we keep on iterating, right? So this is this while loop will keep on iterating until unless there is a break here. Right? If you see, the loop will break when this variable m is equal to 0. Okay, where is m? Here we defined m is equal to 0, right? So m will stay 0 if this for loop is not executed, or if this for loop is executed, this if statement is not true, because we are updating m here. If this update of m, if we do not update m here, so we'll have m is equal to 0 and the loop will break, or algorithm will converge, or we will find the w. Okay, and if you see, this m will be updated if yi w transpose xi is less than or equal to 0. If you remember, if the yi w transpose xi is greater than 0, that is what we require. So if this is the condition, if this is true, it simply means we have a misclassification for xi, or xi is on the wrong side of the hyperplane. So we are iterating, this for loop is iterating over the points in the dataset. So m will be counting the number of misclassifications, right? And misclassification for the chosen point occur when yi w transpose xi is less than or equal to 0. And when we have a misclassification for the chosen point, how do we update weight? So weight will be updated, weight plus yi xi. And what are the possible values of yi? 1, minus 1. Right? If misclassification is due to the point for which the label is 1, we simply add that point to the weight vector. If the associated label for the point for which we have misclassification is minus 1, we simply subtract that point from the weight. And this is a simple perceptron learning algorithm. So we update weight vector, add a point if true label is 1, and subtract a point otherwise. And we keep on iterating until unless we get a hyperplane for which all the red points are on one side and all the blue points with label minus 1 on other side, right? Okay. The question here is, does this algorithm converge, or can we find, or do we always find a hyperplane that separates the data? And the answer is yes. If the data is linearly separable, using this algorithm, we can always find a hyperplane w transpose x equal to 0. Let's build some geometric intuition for this algorithm. Okay, first we talk about how do you visualize w transpose x is equal to 0. If you remember, that's how we defined x. And we note x0 is equal to 1. Right? And this is the weight vector. And if I write w transpose x is equal to 0 in this form, what is this? This represents a hyperplane in d-dimensional space. We have talked about this multiple times. And we know that this hyperplane divides the d-dimensional space into two half spaces. Positive half space, w transpose x is greater than 0, and negative half space, w transpose x less than 0. So there is one more interpretation of this hyperplane. If we consider x0 as a dimension, it means Now my feature space is D plus 1 dimensional space. In D plus 1 dimensional space, W transpose X is equal to 0 would represent a hyperplane passing through origin. Let me try to explain this interpretation. If I treat x0 as a dimension of my data, and I know x0 is equal to 1, and for this two-dimensional data, if I add one more dimension to this, what's going to happen? That dimension is 1. So I can represent the data in this form. So this is x0. I have added another dimension, and we know that the value of x0 would be always 1. So the points, the blue point, red point, and those were appearing in a plane. Now they are appearing on a plane that is placed at x0 is equal to 1. Right? So now we have these blue and red point in a 3D space. Right? And if you see this hyperplane would look like this. So it was a line in 2-dimensional space, but in 3-dimensional space, we know it's a plane. On this side, we have W transpose X greater than 0. This plane is W transpose X is equal to 0. And on this side, we have W transpose X less than 0. So blue point is on the left-hand side of this plane. And the red point is on the right-hand side of this plane. So W transpose X is equal to 0 is a hyperplane in D-dimensional space. It is also a hyperplane in D plus 1 dimensional space, but in D plus 1 dimensional space, the good thing is it represents a hyperplane passing through origin. Right? And we will see what is the benefit of this interpretation very shortly. Okay, for perceptron learning algorithm, for any point xi, W transpose xi magnitude represents the distance of x from the hyperplane. Okay, let me call it xi. How can we show this? First, we note that since every point on the hyperplane satisfies W transpose X is equal to 0, what is the angle between W and any X on the hyperplane? Since W transpose X is equal to 0, how do we define angle between 2 points? Inner product divided by the norm of the individual vectors. And that gives you the cosine of the angle. So if alpha is the angle, and we know W transpose X equal to 0, this implies alpha is equal to pi by 2. Or we can say any point on the hyperplane is orthogonal, is perpendicular to the vector W. Right? That's how we can visualize this. If this is my hyperplane that is separating two classes, so W is a vector that is pointing outwards. So W transpose X is equal to 0 in this region, and W transpose X is less than 0 in this region. Okay, now I go back to the previous point that for any point xi, W transpose xi represents the distance of xi from the hyperplane. We can always express every point xi as a sum of two components. One perpendicular to the plane, other one is parallel to the plane. Any point on the any component parallel to the plane, when you take inner product with W, you get 0. You take inner product with the perpendicular component, that gives you the distance, in fact. the magnitude of this gives you distance. That is indeed W transpose xi, right? Okay, for any point in the positive half space where W transpose x is greater than 0, and we take for any point in the negative half space W transpose x less than 0. If we want to find the angle for these two types of points, what are the angles? Let's visualize this. Say we have this as, okay, you're looking from this side, the W transpose x equal to 0, the same hyperplane. This is the positive half space, this is the negative half space. We have red points in the positive half space, and we have these blue points in the negative half space. You take any point in the positive half space, angle between W and point in the positive half space would be less than pi by 2. Okay? Because all of this space is from within pi by 2 of vector W. And if any point in the negative half space, angle is between pi by 2 and pi. Angle is greater than pi by 2, in fact. Keeping this in mind, we will build the intuition of the perceptron learning algorithm. So we recall that we want to learn W such that yi W transpose xi is greater than 0 for every point in the dataset D. It simply means we are not any misclassification for any point in the training dataset D, or every point is on the right side of the hyperplane W transpose x equal to 0. In other words, we require W transpose xi is greater than 0 when yi is equal to 1, and W transpose xi is less than 0 when yi is equal to minus 1. And we had this algorithm to learn the weight vector W for a given data set. Okay, let's analyze this. We make update when we have misclassification for any point, or when yi W transpose xi is greater than 0. For example, consider a point xi1 for which we have misclassification. So that the label associated with xi is 1. yi W transpose xi is less than or equal to 0 means W transpose xi is less than or equal to 0. Geometrically, it means the angle between W and xi is greater than pi by 2. This xi was supposed to be on the side where W transpose x is greater than 0 because the label is 1. But this point is appearing on the wrong side of the hyperplane. Angle between W and xi is greater than pi by 2. Right? And if we follow algorithm, we will update. We'll update by simply adding a point to the previous weight vector. Right? So W new would be W plus xi. Why do we add? Because the label associated with xi is 1 is positive. What about angle between this new W and xi? Let's call it alpha nu. We note that if you take an inner product with this new vector and xi, that is given by, because W new is W plus xi, W transpose xi plus xi transpose xi, and consequently we can say that W new transpose xi is greater than W transpose xi. So inner product has increased. And we know that the cosine of the angle between vectors is proportional to the inner product. Consequently, the new angle is less than the previous angle. Agree? Okay, let's consider next case when we have a point for which the associated label is -1. So we have a misclassification for this point. This implies W transpose xi is greater than or equal to 0, or the angle between W and xi, my apologies, is less than pi by 2. But we require greater than pi by 2 for xi to be on the right side. So we update W new as W minus xi, and the consequence of this is that the new inner product is less than the previous inner product, and consequently the new angle is greater than, so cosine of alpha new is greater than cosine of alpha, and also alpha new would be greater than alpha because cos is in this range is monotonous. If you see, this is exactly we require, because angle was pi by 2, we want to reduce the angle. Right here the alpha is less than pi by 2, we require alpha greater than pi by 2, so we want to increase the angle. So algorithm is moving in the right direction, or in the direction we want. Okay, let's analyze all of this geometrically. We assume that we have a linearly separable data and we randomly choose W. Say we have this data set and we randomly choose W. All of the blue points, all of the red points are on the right side of the plane, but to one blue point, this one, is on the wrong side of the hyperplane. So we can say we have misclassification for this point only. So our algorithms would detect misclassification and it will make update to the weight vector. In update step, since misclassification is due to the point for which label is equal to -1, so new weight would be previous weight minus xi. So between W and xi, the angle is less than pi by 2, but we require for every xi with label -1, angle should be greater than pi by 2. So we update weight as weight minus xi. Okay, let's analyze this weight geometrically. So this is W, this is xi. So minus xi would be in this orientation, and when you add W, simple using a vector addition rule. So this is my new weight vector. And this is a new weight vector. What about the new hyperplane? Because my hyperplane is defined by this weight vector. This is the new weight vector, and this will be the new hyperplane that is separating the data. Right? And with this hyperplane, when my algorithm iterates over all the points in the data set, it won't detect any misclassification, or we can say algorithm has converged. If you also observe, the angle between this new weight and the point for which we had misclassification is now greater than pi by 2. Right? So that was the geometric intuition and interpretation of perceptron learning algorithm. In the next video, we will formally carry out a proof of convergence for perceptron learning algorithm. We'll stop here and see you in the next video, inshallah. Allah Hafiz.